Okay, in this tutorial we're going to have a look at quartic and higher degree polynomials. Okay, so quartics to start off with, we've got our general form, which is y equals ax to the 4 plus bx cubed plus cx squared plus dx plus e. Okay, so getting a fair bit of terms there, fair few. Hey, and what we find is it generally looks like this quadratic sort of parabola type base shape to it, okay, but it's got a flatter base to it, okay, than what a standard parabola does. Okay, in our stationary point form, which is still our y equals a outside of x take h to the power 4 plus k, okay, we find that we've got this stationary point at hk. Okay. Now we've got an increasing number of intercept forms, which tends to happen the higher the degree you go. Okay, so the higher the degree, the more combinations you've got for your intercept forms. Okay, so our first one is y equals a outside of x take n times x take m times x take p times x take q. Okay, and that's just going to give us our 4 different intercepts, and it could look something like that. Okay, when we have y equals a outside of x take n times x take m times x take p squared, that squared one, again, it's going to be just touching a turning point on the x-axis. Okay, and again, it's squared, so it looks like this parabola type shape. Okay, when we have y equals a outside of x take n squared times x take m squared, we've got 2 of those. Okay, so it just comes down and touches at n and m. Okay, and when we have our last form, which is y equals a outside of x take n cubed times x take m, okay, well at n, we're going to have this cubic type shape happening, okay, because it's cubed. Okay, that's the type of shape that we're going to have for that intercept. Of course, we'll have this other one here. Okay, what does a do for this? Okay, a does exactly what you expect when it's bigger than 0. Okay, it's concave up, okay, like our parabolas, and a is less than 0, it is concave down. Okay, that's all the difference is for our values of a. Okay, so we're going to move on now to some of our higher degree polynomials. Okay, and this is just general terms now. Okay, we could go higher. Our next one is like quintic, for example. Okay, but we're not going to worry about those ones. Okay, so our higher degree polynomials. Okay, so this is talking generally now. So we're talking about when y equals x to the power n, where n is even. Okay, so this is going to be the same sort of form as our quartics. Okay, so we have y equals a outside of x take h to the power n plus k. Well, they'll have a similar shape to a parabola, but as n increases, the flatter the base of the parabola will be. So a quartic has a flatter base, okay, and then as we keep going, it gets flatter again. So here we can see our quadratic, or our parabola, from our x squared. Now the red one is our x to the power 4, okay, and then our blue one is our x to the power 6, roughly. Okay, this is because when values of x between -1 and 1, they give smaller values for y for a higher value for n. So for example, if we had a look at a half, okay, well when we look at a parabola and we square it, we're going to get a quarter. But when we look at a half and we're doing a quartic, okay, well that's going to give a 16th. Okay, so these are our corresponding y values. Okay, so you can see for the same x value, okay, of a half, we get much smaller y values. Okay, and that's going to be even more pronounced when we go to power 6, okay, which is going to be 1 on 64. Okay, so hence this flatter and flatter region between -1 and 1. But then after 1, it's going to shoot up dramatically because, of course, when we go 2 in there, well, 2 squared is 4, but then, of course, our 2 to the power 4 is 16, and our 2 to the power 6 is 64. Okay, so we're going to jump back up quite quickly. Okay, so what will actually happen, okay, is up here somewhere. I haven't really drawn it very well. They're all going to intersect at the points 1, 1 and -1, 1. Okay, and then our parabola, okay, is going to stay outside it. Okay, but then our quartic is actually going to cross back over and come inside. So just exaggerating that flat bottom. Okay, we're going to be something like that. And then our power 6, our next one, would be even, it'd come down lower than that and again come inside this. Okay, so they're going to keep getting narrower and narrower, okay, because of how quickly these jump up. Okay, if a is bigger than 0, okay, then we'll have that concave up shape, and if a is less than 0, then we'll have that concave down shape again. Okay, so again, depending on the form of the function, y equals x to the power n, we'll have up to n intercepts. Okay, now it's going to be true whether it's odd or even. Okay, so I'll just jump over to our next one here, okay, which is talking about y equals x to the power n, where n is odd and n is greater than 1, which isn't true for the other one too. Should have pointed that out. Okay, so we have y equals a outside of x take h to the power n plus k. Okay, well they'll have a similar shape this time to our cubic, or our y equals x to the power 3. Okay, it'll have a stationary point of inflection at hk still. However, again, as n increases, the graph will become flatter between -1 and 1. That's exactly the same reason as what we just spoke about for our even powers. So this time, our cubic's going to look something like this, our red one, and our quintic, okay, is our x to the power 5, is our blue one there, and then our x to the power 7 is our black one. And again, the same thing is going to happen, where these actually this is going to keep skyrocketing up and cross over the other ones at 1, 1 and -1, 1. Okay, that's the points where they're going to have in common. Okay, when we have a look here, if a is greater than 0, then as x approaches positive infinity, y approaches positive infinity, and as x approaches negative infinity, y approaches negative infinity. So really what that means is, as x gets bigger this way, y gets bigger this way, and as x gets bigger this way, y gets bigger that way. Okay, so it's going to have that shape. Okay, and then conversely, if a is less than 0, then as x gets bigger, y gets more positive, y gets more negative. As x gets more negative, y gets more positive. So as x gets bigger in the negative direction, y gets bigger in the positive. As x gets bigger in the positive, y gets bigger in the negative. Okay, and again, depending on the form of the equation, y equals x to the power n, where n is odd, can have up to n intercepts. Okay, so same thing. Doesn't matter whether we're an even or an odd power. Okay, so I've just got one example that I want to show you. It's a little bit different. Okay, so we've got sketch y equals x to the 4 plus 8x squared take 9. Now, for anyone that's watched my cubic video, okay, they might be getting a little bit worried here that we're going to have to do a fair bit of division of polynomials, but I wanted to show you this one because we don't actually need to do that. Okay, we can do a sneaky little substitution. So what we can do is actually say let a equal x squared. Okay, nice little trick to do here. Okay, and again, this trick I think I showed in a different tutorial as well, as one that you really need to get your head around because it's useful for a lot of different forms of our equations. It's likely to come up on an exam as well. So when we do that substitution, it means that we get y equals a squared plus 8a minus 9. Okay, so now we've got a quadratic, okay, and a quadratic that we can factorise. Okay, so we should be looking at here, we should be able to factorise this one. Okay, so we need to be a take 1, and a plus 9, okay, so that we multiply to get -9 and add to get positive 8. Okay, at this point we can go ahead and substitute back in our x squared, so we can say now we've got x squared minus 1, okay, we've got x squared plus 9. Okay, and sorry, I just realised that should have been a positive as well, otherwise we're going to have a problem here. Okay, that needs to be a positive. Oh, we're changing things around all over the shop here, hang on. Oh, sorry, because we needed this to be a negative. Okay, and that's going to change this. This really needs to be plus 10. Okay, so you'll see what would have been a problem in just a minute. Okay, so here, okay, we're wanting to find our x-intercepts. That's really where we let y equals 0. So we're going to solve this. Null factor law means that we can say that x squared minus 1 equals 0. Okay, oh, I should say, and x squared minus 9 equals 0. Okay, so that means that x squared equals 1, or x squared equals 9. Now, if I had left this as my positive in here, okay, well, we've been saying x squared equals -9, and we can't take a square root of a negative number, so we would have put ourselves in trouble there. Okay, so we can say then that x equals plus or minus 1, and x equals plus or minus 3. Okay, so they're going to be our x-intercepts. So we can go ahead and look at graphing this now. Okay, so we can say that we've got, I'll give myself a little bit more room here actually. Okay, so we can say we need to have it this scale right, so we can say now that that is going to be 1, 2, 3, okay, minus 1, minus 2, minus 3. Okay, so for this example, we need to think about what our A value was. Our A value was 1. Okay, so that's bigger than 0, so we're going to be concave up. So we're going to be looking like that overall. Okay, but of course we've got our 4 intercepts. So we're going to be coming through here. Just knowing this means that we know we've got to come down here. Okay, and we've got to come back up here, we've got to come down there, and we've got to come back up here. Okay, so we're going to say we're doing something like this. Okay, because of the symmetrical nature of this equation, we would know that they're going to have the same values down there, which we don't know what that is, but that's fine. Okay, when we want our y-intercept, we just left x equal 0, so we know that that is 9. Okay, and this would be our turning point up there. Okay, because of a bit of symmetry happening with this one. Now, often with our Quartics, we won't necessarily have that symmetry. It's just this example that's doing it for us. Okay, and again, we're not too worried about what our actual values are here. Okay, of course, we could work it out by subbing the value back in. Okay, but we won't worry about that too much at the moment. Okay, we're not really that fussed. Okay, so that would be that example there. Okay, so just did one little one for you with this one. It's very similar to our other processes, with it being our cubics or or our quadratics. Okay, very similar process. So hopefully that'll be enough to get you through some of the questions on this sort of topic.